monoalphabetic cipher. We are going to discuss about another kind of substitution cipher, which is monoalphabetic cipher. Monoalphabetic cipher. And possibly we try to break this cipher by using a cryptanalysis called frequency analysis. Okay, so we'll do the cipher cryptography as well as cryptanalysis of monoalphabetic cipher too. Okay, so what is this monoalphabetic cipher? This monoalphabetic cipher is a kind of substitution cipher. Okay, it's a kind of substitution cipher. It is based on substitution again. Okay, each character to be replaced by other character. Okay, but CC cipher is also a substitution cipher. The occurrence of a character, a single character, to be replaced by one specific character based on the key. Okay, so the key is common to the entire plain text. Key is common to the entire plain text. Okay, so that's why CC cipher is breakable just by trying 26 keys. Okay, so key space is very small with CC cipher. That's why it's breakable. It's not possible to use it for any low-level security at all. Okay, so we need a crypto system like a simple substitution cipher, but the key space should be very large. Okay, so monoalphabetic cipher is a type of substitution cipher, but key space is very large. The idea behind this is we are going to use a key. The cipher is a substitution cipher. Okay, so key is selected as one of the permutation. Okay, so for example, if you take an alphabets of three, a set of three elements, just three elements, A, B, C, a set of three elements. Okay, so how many possible permutations are available with these three elements? We have a set of three elements. Okay, what are the possible permutations? A to be replaced by A, B to be replaced by B, C to be replaced by C. This is one possible permutation. A can be replaced by B, B can be replaced by C, C can be replaced by A. This is another permutation. Okay, so B may be replaced by C, B can be replaced by C, and C can be replaced by A, and B can be replaced by B itself. So in this manner, how many unique permutations are possible with this set of three elements? How many unique permutations are possible with this set of three elements?
6, ma'am.
That is nothing but 3 factorial. Okay, so first you can have the option of n-1 different combination, then n-2 combination, then n-3 combination, so on so on. So this is a set of three elements. So 3 factorial permutations are possible. Okay, but if you take an English alphabets, it's a set of 26 characters. Okay, so A, B, C, and so on. The set of 26 characters. So how many unique permutations are possible? So there are 26 factorial permutations are possible. The 26 factorial is a very large number. It's order of magnitude of 10 into 2 power 26. So this is very large. Okay. So here the key, what is the key? Key is nothing but key is a permutation. One of the permutation. One of the permutation. Key is not a character. Key is one of the permutation. Okay. So how many permutations are available? 26 factorial permutations are available. So here key space is 26 factorial. So this 26 factorial permutation is not breakable by using brute force attack. Okay, so hacker, it is not possible to try all the combinations of permutations by trying 26 factorial permutation for the given text is not at all possible. Okay, so here we have a very large key space as compared to CC cipher. So a brute force attack is not possible. That is ciphertext only attack is not possible. Ciphertext only attack is not possible. Okay, but a different type of attack is possible. That is known as frequency analysis attack. That is known as known plain text attack. I'll tell you later. But before that, let's get into one simple example here. Let's take a key. A key is one such permutation. Okay. So, for example, in the English alphabets character A, E, C till we have insert. Okay. So A to be replaced by one specific character is. There is no relationship between the orders. Okay. You can take any arbitrary permutation. B can be replaced by C. C can be replaced by Z and so on. Okay. So key is the permutation. What is a key? X, C, Z, and so on. Let us assume this Z is replaced by Sandhya. Okay, so this is the key. This key is agreed between Alice and Bob. Okay, so here the key is not a arbitrary length word. Key is a 26 letter character, 26 unique letters. Okay, so that permutation is agreed between Alice and Bob. Okay, one single permutation is agreed between Alice and Bob. Okay, so the encryption process here is applying the permutation. For example, my plain text is Sastra. Okay, so if it is so, the S to be replaced by, let us assume in this character, S to be replaced by some E and A already here, and T to be replaced by some character like O, R to be replaced by each occurrence of A replaced by X. Okay, X appears two times, so same character to be replaced. T to be replaced by O, and R to be replaced by A, and A to be replaced by X. This is a ciphertext. And this permutation is known to analyze Bob also. Okay, so Bob will use the same thing. The P will be the plaintext character. The P will be recovered back by doing the reverse substitution. P will be substituted by S. Each occurrence of P is substituted by S, same character. Okay. X, each occurrence of X to be substituted by A. Okay. And each occurrence of O to be substituted by T, so T, and A to be substituted by R. Okay. So here the key is a single permutation out of 26 factorial permutation. So this is a type of monoalphabetic cipher. A very simple cipher. It's a block cipher. It works on a block of character. It works on block of character data. Okay. So in this case, brute force attack is not possible, but the next subsequent attack is the frequency analysis attack. Okay. Subsequently, we are going to discuss about the next consecutive cipher, which is an improvement of monoalphabetic cipher, that is known as polyalphabetic cipher. So monoalphabetic cipher or polyalphabetic cipher or Cipher cipher, all those ciphers are vulnerable to frequency analysis attack. That is very simple attack. Okay, so I will tell you that frequency analysis attack with the example. Okay, for crypto related stuff, so many websites are available. Okay, so then and there I will introduce those websites also. Okay, because so many problems, auto problems are available. You can prepare for placement, security related companies placement by using those crypto stuff. Okay, so today I'm going to introduce one website, CryptoCorner. Okay, so you can use this website to solve specific problems. Okay, some automated tools are embedded here, so you can solve it, and you can also learn the method, the basic methodology of each and every problem statement. Okay, so here we are going to break a code by using frequency analysis. Okay, so most of these websites are having an embedded tool. Okay, so if you type the text here, automatically it will encrypt it. Okay, but that is not required. Okay, because you need to know how to do this. Okay, so let's get into this. Just I have a text from our Williams Challenge book. Okay, just copy it. Now, if you paste it, it will do the frequency analysis attacks. Okay, by doing all these things. Okay, so but I'll tell you what is the method behind this. So this frequency analysis attack is based on by exploiting the property of the language, okay, the basic aspects of the language. So this monoalphabetic cipher is applicable for English alphabets. Okay, just by exploiting some of the basic properties of English alphabet, we can do the analysis. We can break the crypto system. Okay, and normally classical cipher, all the classical ciphers are based on English alphabet. But modern ciphers, I said I repeated so many times, not based on English alphabet, it is based on. And moreover, it allows different type of languages, different set of languages. We can use Sanskrit-based crypto system or Hindi-based crypto system or all those things. But the frequency analysis attack here, we are going to exploit English language properties. Okay, so the same monoalphabetic cipher is possible with other language. You can do it with Hindi or some other alphabet, some other character set. You have to exploit that language properties to break the cryptosystem. Okay, so here we are going to exploit English language uh, uh, basic properties to break this cryptosystem. Okay, so if you take the language English, the occurrence of each character. Okay, so the if you take a paragraph of text, okay, the paragraph of text for every 12 character, definitely you can find one E. Okay, so E is the most common character in English language. E is the most common character. Okay, even actually monoalphabetic cipher is not for breaking a single word. You cannot break it by using single word. Input will be the paragraph of text. Okay, so if the number of characters are high, the possibility of breaking the cryptosystem is high. Okay, so one major property of English language is E is the most common character. Okay, the next most common character is T. Okay, then subsequently A, O, and so on. So this is a frequency table available for English language. Okay, so you need to know this. In examination point of view, for cryptography, so many extra material will be given for solving the problem. Okay, so this is one material will be given to you to solve monoalphabetic cipher. In the question paper, the university exam question paper, if you have a problem related to monoalphabetic cipher crypt analysis, this is a material will be given. No need to memorize it. Okay, so this is a frequency table of English alphabets. Okay, so E, the most frequent character, T, the most frequent character, and so on. Okay, and in the similar manner, the English alphabet, we have some most common diagrams. For example, TO2 is the most common diagram. Okay, and AN is the most common diagrams. Okay, so IT is a highly most common diagram. So some diagrams are also very frequent. Okay, some diagrams are not at all possible. Okay, because all these are sensible words, you know. So yes, yes, not a meaningful word. TT, not a meaningful word. Okay, so some moreover, the same character may not be repeated. Okay, so TT, SS, OO, all those are not a meaningful diagrams. Okay, so we have some frequent diagrams that is also listed. And some common trigrams are also available. THE, very common trigram. ONE, the most common trigram. Okay, A and D, most common trigram. In similar manner, we have 4-letter set, 5-letter set, and so on. Okay, just by solving the pseudo core jumbo in the sentence, you have to solve this. Okay, so let's get into a simple example here. This is a paragraph of text. Okay, this is a paragraph of text. Is it visible to you? Is the screen visible to you? Crypto Corner web page, is it visible to you?
Yes, ma'am.
Okay. So this is a paragraph of cipher.
Yes, ma'am.
Nothing. Okay, good. So nothing is meaningful. Okay, so we have to make it as a meaningful paragraph by applying frequency analysis attack. Okay, so the first step here is for every character. So let's take G. Okay, for this character. So first of all, totally count the total number of characters. Let it be the total number of characters is 1000. Find out the relative frequency of each and every character in the 1000. Okay. Say for example, count number of occurrence of G, number of occurrence of G divided by the total number of characters. Okay. So for every alphabet character, count the number of occurrence. Okay, and relatively calculate the frequency of occurrence of the character in this paragraph. Okay, so what is the procedure? How many times G appears here? Just to count it, divided by the total number of characters in this paragraph. Okay, so you have to do it for all Z characters. Actually, this frequency analysis attack is not possible for hand-coded calculation, but it will be. It is very easy to solve this type of problem with a normal computing problem. Okay, so occurrence of each and every alphabet character in this cipher text okay, to be calculated. Okay, so that is calculated here. Let's see. A appears only 5 times in this particular paragraph. This is cipher text. Okay, A appears only 5 times. B appears only 2 times. C appears 26 times. S appears 88 times. O appears 85 times. Okay, just find out the occurrence of each and every character. Then draw the frequency diagram for this decrypted character. Okay, so this is actually English standard frequency diagram. Okay, so this is actually our decrypted, encrypted data frequency diagram. Yes, appears 88 times. Okay, the highest, the character, the most frequent character in this cipher text is yes. Okay, the next most common character in the cipher text is also just create a short text. Okay, so now what we have to do here is the most common character, this yes, probably it will be the most common character in this standard alphabet E. Okay, so wherever there is yes, replace E. Okay, so wherever there is yes, replace E. So that all the 88, here we have 88, yes appears 88 times. Okay, all the 88 character can be replaced by just by using single substitution, replace this by E. Okay, and the next most common, because the difference the next common character is G, but the difference is somewhat wider. Okay, so normally the most common character is C, the subsequent character will be always be, most of the time it will be A or T. Okay, so replace this by the next most common character. Okay, so actually when you replace it, here also you have to use some common sense. Okay, first you have to replace all the yes to be yes to be replaced by E. Okay, so if you replace it, you will get a character like this. All the yes are replaced by E. Okay, so the next most common character also replaced by T. Okay, because T is the next most common character. Small case letters are decrypted character. Okay, all the capital letters are original character. So each occurrence of E is replaced by, each occurrence of S is replaced by E. The next most common character is O. So all occurrence of O is replaced by T here. Okay, so H and T. Okay, so now you have to do it some parallel task. Now you can go for the next most common character. In addition to that, you can also think about replacing the diagrams. Okay, so now here just check it out the diagrams. Here we have one diagrams. Here we have one diagrams. LG is one diagram. MF is another diagram. WE is another diagram. TG another diagram. In this partially filled diagram is this. Okay, because one character is already filled, which is T. Another character yet to be filled. Okay, G. So the most common thing is that the most common diagram will be T O. Okay, so you can also use a frequency analysis. Sorry, the frequency of occurrence of the same character again. Okay, so T to be replaced by O. Sorry, G to be replaced by O. So wherever there is G, you can replace by. Okay, so this G is also replaced by O, and this G is also replaced by O. Okay, not a single character, because each character is replaced by one specific character. But what we have exploited here, we have exploited diagram principle, most common diagram. Okay, so this G to be replaced by O, so TO is a meaningful diagram, and wherever there is a G, replaced by O. Okay, so this G will also get replaced by O based on the frequency of diagram. So most common diagrams. Okay, and then you can go ahead with the most common diagrams. Okay, so if you replace G by O, this will be O F E. O F E. Okay, so O is a decrypted character, E is a decrypted character. In between, we need one character. So the most common diagram to be used here. Okay, so the most common diagram with starting character O, ending character E. So very simple, it will be one. Okay, so all the F's are replaced by F. Okay, so in this manner, you have to exploit the frequency of appearance of a character in the English alphabets. Parallelly, try to replace the diagrams and trigrams. Whenever you replace the trigrams and diagrams, the appearance of the same character to be filled in the remaining part of. Okay, so by exploiting diagram principle, you will get this, because this is replaced by TO. So there is wherever T followed by G replaced by TO, and all the G's are replaced by. Okay, now trigram principle, OFE is be replaced by OFE. Okay, so if you replace F by N, so it's common for all. Okay, so here THE followed by F. The most common four-letter character is also then. Okay, then or they. Okay, both are possible. Just trial and error. It is also probabilistic approach. Okay, so those character to be replaced, F to be replaced by N, if you replace f by n, okay, all the occurrence of f to be replaced by, because most of the character, so many f's are available to them, so those f to be replaced by n. Okay, and then you have to proceed further with the 5 letter character L H E E encrypted character, decrypted character. Okay, L is not it to be encrypted. Okay, so the meaningful word out of this is probably L to be replaced by yes. Okay, so wherever there is L, replaced by yes. Okay, so in this manner you have to proceed. So here SODVE, decrypted character, DV is encrypted character, DV to be replaced by 2 other characters. Okay, so most of the common thing is meaningful word is solve. Okay, so D to be replaced by L and B to be replaced by D. Okay, so wherever there is D, replaced by L, and wherever there is D, replaced by D. Okay, so in this manner we can slowly progress and we can get the final result like this. Okay, so this is for the final decrypted character. Okay, from this decrypted character, you can derive the permutation. You can derive the key. Okay, so the key used here is simply derived here, because crypt analyst need to find out the key, not only the plain text. Okay, so the key here is a permutation. The permutation is A B replaced by M, B is B replaced by A, and so on. Z is replaced by Z. This is for the permutation used by the analyzer block for encryption. Okay, so this frequency analysis attack is very common. It's possible with the normal computing power. Even if the plain text of size 100 characters are available, then you can easily solve this by applying the properties of English language. Clear? You have to work out only once, then you can get a better result. Clear? So this is not ciphertext only attack, because we need extra data. Okay, so the extra data is frequency table and also other kind of stuff. There is the most common diagrams and trigrams. So all those things are available. So that this is not ciphertext only attack. Total analysis is extra data. Okay, so this type of attack is also known as known plain text. Some of the things are already known plain text attack. Clear? Any doubt related to frequency analysis attack? Because this is important. Enhanced version of the frequency analysis attack to be applied for polyalphabetic cipher. Okay, for polyalphabetic cipher, we will try it out in the example in the whiteboard. Okay, is it clear? Shall I proceed further?
Yes, ma'am.
Okay. So now we get into the next type of cipher, which is known as polyalphabetic cipher. So here, CC cipher, the problem with the CC cipher is the key space is small. Okay, so that we started using monoalphabetic cipher. In the monoalphabetic cipher, the lesser small key size is reduced by using a different permutation. Key space is expanded, the student is factorial. But the problem is it is vulnerable to very simple attack frequency analysis attack. Okay, so we have to make a crypto system. The next innovation is an extension of monoalphabetic cipher with resistance of frequency analysis attack. Okay, this simple frequency analysis attack. Okay, so in what way we can reduce or we can avoid or we can resist frequency analysis attack in the monoalphabetic cipher, which makes the frequency attack possible? Which property? Which property of monoalphabetic cipher leads to the use of frequency analysis attack, or leads the loophole for frequency attack? Which property? What's the basic property here?
Substitution.
Substitution. CC cipher is also based on substitution. Okay.
Substituting distinct characters.
Substituting each character by one specific character. All the occurrence of one character is replaced by a same character. That is what the vulnerability of monoalphabetic cipher. So, because that property allows the use of frequency analysis. Because what we did, we have taken the most common character as a replacement character. Okay, so we can avoid this. We can resist the frequency analysis attack by replacing this occurrence of the different occurrence of the same character to be replaced by different character. I'll repeat again. All the occurrence of a single character is replaced by one specific character. What is it? Yes, yes. Okay. Yes appears 2 times. Okay. Yes. All these occurrence of yes replaced by P. Okay. So this makes frequency analysis attack possible. Okay. So what sort of change we can make here? Each occurrence of the same character to be replaced by different character. That means the first occurrence of P, first occurrence of S to be replaced by P. Second occurrence of S to be replaced by some other character. Okay, so if you replace like this, for example, the first occurrence of S is replaced by P, and the next occurrence of X is replaced by something else, Y. Okay, so if it is so, the frequency analysis attack is not possible, because it is not possible to find out the most common character in this ciphertext. Okay, because here the most common character is yes, but but the same character substituted by 2 different characters. Okay, so it is not possible to find out the most common character in the ciphertext. Okay, so that is the property required for a substitution cipher with the resistance of the basic frequency analysis attack. Okay, clear? Can you understand my point? Please be interactive. Can you understand my point here?
Yes, ma'am.
So, each occurrence of the same character to be replaced by some other character. So, that type of cipher is known as polyalphabetic cipher. Okay. So, polyalphabetic cipher. The next type of cipher, next extended version is known as, this is also a classical cipher, polyalphabetic cipher. Okay. But the reason behind this is the monoalphabetic cipher it's vulnerable to frequency attack. That's why we designed this. Okay, this is also vulnerable to an enhanced version of frequency analysis attack. Okay, not like a simple frequency analysis attack like this. It requires some sophisticated frequency analysis attack, which was developed by Kaspersky technique. That is not actually frequency analysis attack, that is Kaspersky technique. Okay, so this is also vulnerable with a sophisticated attack. What is a sophisticated attack? Some extra effort is required. For a frequency analysis attack, extra effort is not at all required. Okay, for CNS cipher, extra effort is not required. But for polyalphabetic cipher, to break this polyalphabetic cipher, some extra effort is required. That is an advanced version of frequency analysis attack by Kaspersky. Okay, so I'll tell you the cryptanalysis later. But before that, what is this polyalphabetic cipher? Okay, so there are different types of polyalphabetic ciphers are available. One cipher, this is also substitution cipher, not based on any permutation or transposition. It's a substitution cipher. Each character to be replaced by some other character. Okay, so this is actually this type of cipher developed by the scientist called Vigenère. So the cipher is also known as Vigenère cipher. Okay, because this cipher is developed by Vigenère. So this is also known as Vigenère cipher. Okay. So the input, the idea here is each alphabet to be replaced by the occurrence of same character to be replaced by a different character. That is what the requirement here. Okay. So this is based on a simple mathematics. Let us take a plain text. Okay. So plain text is a set of characters. Okay, that will be P1, P2, and so on. N character set with the length. Okay. So if it is encrypted, definitely the ciphertext size is also a character of length N. Okay. So C1, C2 till Cn. Okay. So for this, we have to use a key. So key is also a set of characters, mean or Bn. Okay. Maybe K1, K2 till K. Okay, m can be less than it's very smallest compared to n. That is also possible. Okay, m will be less than. So P plain text is a character of length n. Ciphertext is a character set of length n, and key is a character set of length e. Okay, so encryption process here is encryption on each character. Encryption algorithm to be applied for each character separately. PI, we take each character, and also take each ciphertext character. So this is equal to encryption is equal to PI plus K. Actually, you cannot use I here because this length is different and this length is different. Okay, so PI, and I can use this as, or otherwise I can do like this, Ki mod delta 6. Okay, so the whole thing mod delta 6. Okay, so for example, P0 plus K0 mod delta 6. Okay, let it be M is equal to 5, N is equal to 10. Okay, otherwise N is equal to 8. Okay, the plain text is of size plain text is of size 8 character. Okay, ciphertext key length is of 5. Okay, so P0 plus K0 mod 26. Then how many plain text characters are available? P1, P2, P3, P4, P5, P6, P7. So C0 is this, C1, C2, C3, C4, C5, C6, C7. Okay. Now here this is P1 plus K1 mod 26, then P2 plus K2 mod 26, P3 plus K3 mod 26, and C4 is equal to P4 plus K4 mod 26. Sorry, this is not this is equal to, yeah. And C5 is equal to P5 plus the size of the K is a 5-character word. Okay, so K is made up of 5 characters, K0, K1, K2, K3, K4, 5 characters. Okay, so after applying K4, how to come back again with K0. Okay, so this P5, how to use it? K0. So that is what I mod M. Okay, so what is it? I is nothing but 5. So 5 mod 5, 5 mod 5 is equal to 0. Okay, this is K0. And here I is 6, 6 mod 5, 6 mod 5 is 1. Okay, so then K2 and so on. Okay, so mod 26, every time do the mod reduction on 26. Okay, so the length of plain text is 8 character, the length of the key is 5. After the fifth character, the key, just circular repetition, the K0 to be applied. Okay, so for decryption operation, the same thing, just like a CNS cipher. Okay, instead of addition, use the additive inverse. Okay, so D of Ci comma Ki is equal to Ci plus Ki mod M. Okay, so the whole thing Ci minus Ki is subtraction operation, additive inverse is subtraction. Ki mod M, the whole mod 26. Okay, so P1 is equal to C1 minus K0 mod 26. C5 is P5 minus K0 mod 26. So this is for this decryption operation. Okay, or simply I can write like this. For example, if my plain text is, for example, if your plain text is Sastra University, just write down the plain text. Okay, my key is let it be the key is red. Okay, let it be red. RED. What we have to do here is repeat again and again. Okay, for these 3 characters, red to be used. For the remaining 3 characters, same red to be used. For this, these three are ED. For these three are ED. For these three are ED again. For this, okay. So now here these two are solved by using simplicity is a cipher. Okay. So yes is used as a plain text, R is used as a key. Okay. Yes, its equivalent integer position. What is equivalent integer position? Yes, equivalent integer position in the alphabet. Start with the
18,
0. 18. R is equivalent integer position.
17,
Okay. So 18 plus 17 more 26. What is the result? 18 plus 17 more 26.
9,
9. So ciphertext is ninth character. What is the ninth character? Start with the 0. What's the ninth character? What is the
J,
ninth character? J. So yes to be replaced by J. This yes to be replaced by J, but this yes to be replaced by some other character because we are going to use D as a key size. Okay, so each occurrence of yes is replaced by different character. Now this yes is adjusted, shifted with a position of 17. This is a shift cipher with a key 17. Okay, so this is again a shift cipher with a key 5 because D alphabet is used here as a key. Okay, for this yes, okay, replaced by this yes, these two, and this is also replaced by. Okay, but here I have used a very small key so that the repetition of R appears here. That is here by chance. I use a very small key. Okay, but what is the major requirement of polyalphabetic cipher? Each occurrence of S to be replaced by a different character. Each occurrence of the character to be replaced by a different character. But what happened here? This S is also be replaced by same character R. That property is exploited for cryptanalysis. Statistical technique. Okay, that property is exploited for solving the situations for making a cryptanalysis of monoalphabetic cipher, polyalphabetic cipher. That is the statistical technique. Okay, if the key stream is very lengthy, then that attack is not possible. Okay, so now let's see this. Now it is also known as dictionary cipher. The reason is uh, instead of doing this arithmetic, for example, your plain text is a plain text is a paragraph of size 1000. Every time you have to do one. For every character, you have to do one addition and one model reduction. Okay, model reduction requires some division. Okay, so addition reduction for every character seems to be a time complex operation. Okay, as it is a substitution cipher, we have to substitute each character by another character directly without using any computation. Okay, that's possible by using one equivalent table called viginary table. Viginary table can be constructed. See, I tell you, the same cipher can be implemented without doing this arithmetic. Okay, that is based on a table called viginary table. Okay, so I'll tell you how to construct the viginary table. Viginary table. Okay, so the viginary table can be easily constructed. It is like 26 rows, 26 columns. Okay, as 26 are rows, 26 rows, 26 columns. Each row to be filled with a unique alphabet, the alphabetical order A, B, C, D, E, and so on. So this is see, and each column A, B, C, D, E, F, and so on. Okay, so now this one to be filled with, now this column to be filled with the C cipher with the key 0, shift the key 0. And this column to be filled with the C cipher with the shift key 1. This column to be filled with the C cipher with the shift key 2 and so on. Okay, that is hard. That is also, it won't require any computation. The shift key with 0 means it will appear as it is A, B, C, D, E, and so on. Okay, now here A to be shifted with two characters, so this will be B. Okay, now B to be shifted with two characters, so it will be C. C to be shifted with two characters, D. D to be shifted with two characters, D, and so on. Okay, now again this will be C, and this is D, and so on. Okay, you have to complete this visionary table. Okay, clear? I will show you the visionary table in the Google because it's one common table here. Okay, this is what the dictionary table. Can you able to see the table? Please take it out in your notebook. This table alone. A, the first column to be filled with the CC cipher with the shift C. Okay, then shift 1, shift 2, shift 3, and so on. Okay, the entire each and every row is indexed by English alphabet A, B, C, D, E, F. Okay, take it out the table at least partially. Taken. Please take it out in your notebook. Then I will tell you how to do the encryption and decryption by using a simple lookup. Okay, this table is used for encryption as well as decryption. A simple lookup. Okay, I've taken this. Okay, can you able to see this dictionary table? Is it visible to you?
Yes,
So
ma'am.
how to do the encryption with this dictionary table? So encryption, decryption, both are a simple lookup. Okay, so this is actually a dictionary table made upon ships. But anybody can do this. Okay. So now they have to do the encryption and decryption process, encryption and decryption. Okay. So for encryption, let us take my plain text as plain text. Okay. Sastra, Sastra, and this is Redred. Okay, K is red, red. Okay, this is plain text, and this is okay. So what we have to do here is we have to take it out these two characters. Okay. Now take it out the plain text character and the key. Okay, yes or alone. Okay. So yes is used as the column index. Okay, just go to this column. Now here we have the column index is. Okay, go to this column, and R is used as a row index. Okay, so in this row, take it out the corner character. What is the corner character? Corner one here. What is the corner one here? Yes and R. Is it J? Is it J? Can you able to get the corner character as J?
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
That is what we decrypted already. We did just by using addition and subtraction, we got J. Okay. So by using lookup, you're also getting the same character. The character here is G. Okay. So in this manner, each and every character can be encrypted. Let us take A and E. Okay. A is used as a column index. E is used as a row index A and E. So this character to be used here. So this is in this manner you have to encrypt. What is the decryption process? So decryption, the same lookup table uses, no separate table. Decryption, for decryption process, you have to use the same table. Okay. For decryption, you will get two input. What are those? Key and ciphertext, J and R. Okay. So what you have to do here is the same thing, but a different lookup. Go to the key row. Okay. So R row, this row. Okay. This is a decryption process. Go to the key. Go to the row with a key character R. Okay. So now we have to scan through this row until you get the cipher character. Okay. Now the cipher character is J. Okay. After getting the cipher character, its column index is used as the plain text. Got it? Just originate table is enough to encrypt a character of any length for monoalphabetic set. Okay. For plain text to ciphertext, plain text is used as a row ID. Ciphertext is used as a key is used as a column ID. You have to find out the corner intersecting character. That is encryption process. Decryption processes use the key to find out appropriate row. That scan through the row until you get the cipher character. Once you reach the cipher character, its column head is a plain text character. So column head is yes, that is a plain text character. Clear? Clear with visionary cipher? So visionary cipher, you can do it in any two different forms. One is by applying addition followed by modal reduction. Pi plus Ki mod m, the whole mod 26 for every character. Another thing, you can construct the visionary table like this, and encryption, decryption is simply a lookup. Okay, the character, appropriate character to be extracted from this table. But you need to know the way of lookup. Okay, so here the lookup is plain text is a row ID, key is a column ID. Here, key is used as a row ID, and the appropriate ciphertext is used to find out the column index. Okay, here, any doubt? So in this case, the problem is it completely we resolved the thing called frequency analysis attack. Okay, but here there is again a chance the same character, yes, the first character is shifted with the position R. The second occurrence of S is shifted with the position B. Okay, the third occurrence of S is by chance it is shifted with the key sub D. Okay, this property is exploited to make a cryptanalysis on this. That cipher is known as, so that type of attack is known as enhanced frequency analysis attack. In enhanced frequency analysis attack, the major requirement here is this displacement. The counting the displacement, the length of the key, finding out the length of the key itself is a first process, sophisticated process. Okay, so once you know the key length, inside this, each and every character is replaced by the same character. So finding out the key length is something important. Okay, so the key length is evaluated. Key length is also secret. Okay, so key length is estimated based on the displacement technique. Okay, so the entire cryptanalysis is proposed by Kaspersky technique. We'll talk about this the next class. Okay, again, it's a type of frequency analysis attack with unknown key length with polyalphabetic style. Okay, but because this Kaspersky technique, this frequency analysis attack is somewhat lengthy process. It needs someone to solve this, so that I will shift this topic tomorrow. But moreover, we can also enhance this polyalphabetic cipher with the resistance of this Kaspersky technique by doing a simple add-on. Okay, that is known as auto key visionary cipher, auto key system or auto key visionary cipher. What is it, auto key? That is very simple. The key to be used only once. What is the key? Red. Red to be used only once. Okay. The following character, the key should not be repeated because the repetition leads to Kaspersky analysis. Okay. So instead of repeating this character, the key should also be, the key stream should also be, the length of the key stream should also be equal to the length of the plain text. Okay. But it is not possible to remember lengthy key. So the simple technique here is, after this RED, after completing the key, the remaining character to be filled with the cipher character. Okay, so for example, here SAS is replaced by, let it be SAS as SAS with RED. I'm getting JEC. So now subsequently this is replaced by JEC. Subsequently character to be replaced by JEC. Now if you encrypt it, you will get some X, Y, Z. So this three character to be replaced by X, Y, Z. Okay, so the key string is also very unique, lengthy, based on the size of the playlist. The JEC is based on the previously computed ciphertext. Okay, so I can generalize like this. I can generalize like this. Okay, for example, your key size is 3, K0, K1, K2. Okay, after that, C0, C1, C2, C3, C4, C5, and so on. Okay, so you will get a unique key string here. Okay, so this type of system is known as auto key system. For auto key system, the Kaspersky technique is not possible with the frequency analysis attack. Advanced frequency analysis attack is not possible with auto key because every character will be replaced by some other character. Okay, so just by exploiting the length of the key, we can break monoalphabetic cipher by applying Kaspersky. But that is also removed by using auto key visionary cipher. In auto key visionary cipher, use the key only once, but after that, use a previously computed ciphertext for lookup. Okay, not plain text, ciphertext. Okay. Here, any doubt related to this? Any doubt? Okay. So I'll stop here. Tomorrow we get into the advanced frequency analysis technique with visionary cipher, which is SSK technique, finding out the length and solving cryptanalysis based on frequency. Okay. So what are the cipher we discussed so far? Caesar cipher, Hill cipher, flavor cipher, monoalphabetic cipher, polyalphabetic cipher. Okay, so that's it. These are the common classical substitution ciphers. So after completing the frequency analysis attack, we get into the permutation based cipher. Okay, so I'll stop here. If you have any doubt, you can ask.